Week 8, we continue with some exercises, just as I told you a couple of minutes ago. And I'm going to cover this I'm going to continue covering this e to the x example with more detail. Well, before getting to this example, I'll try to explain something that I've been trying to explain for a while, but again, didn't get into much details, but which I will now. I'm going to talk about the concept of fixed point decimals. Well, you know what a decimal number is. Let me write a decimal number, guys, on screen. So this is a decimal number. So this is a decimal number, 9.1. This is a decimal number. In mathematics, you can easily say that this is 9 times 10 to the 0 plus 1 times 10 to the minus 1. And it goes on like this. Any number goes on here, goes something like minus to the n. And if you put numbers here, it has the multiplier n to the plus n. I guess you have no problems with this. Okay. So imagine, how do we do the calculation on decimal numbers? I mean, this may sound a bit trivial to you, simple to you, I understand, but these are the things you have been doing, I mean, by heart. You're doing them so automatically that maybe you forgot how to get into the details of it. Because when you were a child, like 10-year-old child in primary school, you have given attention to these. Since we are going to do the same operations on hexadecimals and binaries, there are things that we should again give some attention to. Just like I'm writing a decimal number in base 10. And you want to sum up and with another decimal number plus. The easiest way to do this is, let's use 3 digits after the right to the decimal point. To put the decimal point, I mean, aligned with the decimal point and write the numbers. Sorry. So that each digit will be aligned, right? Because when you do this way, what happens is basically, I mean, it's something very simple, but actually these digits have the same multipliers, because these have the multiplier 10 to the minus 2. These have the multiplier 10 to the minus 1. This only one has the multiplier 10 to the minus 3. That's why we put a 0 here. This one 10 to the plus 1. This one 10 to the plus 2. Zeros, if we write this, 10 to the plus 3. And these guys 10 to the plus 4. Any problems with this mathematical thing? I mean, I'm trying to remind you something, because it's a bit stupid way of putting it this way. So I hope you're not confused. I mean, it's not something that you won't understand, but I can confuse you. I hope I didn't. So guys, actually, in binary numbers, it is just the same, because binary numbers is base 2, decimal numbers is base 10, and hexadecimal numbers is base 16. So let me write a number. So let me write a hexadecimal number. Where is the dot? I decide where is the dot. Imagine I decide that the dot is here. The dot is here. In that case, the multiplier for this one is, gerçekten şu kalemi neyse, yani birkaç hafta öncesine göre iyiyim de, 16 to the minus 1, because this is base 16. That's what hexadecimals are called. 16 to the 0, 16 to the 1, 16 to the 2. Bir önceki example'da 10 üzeri 0 yazmış mıydım ya? Yazmadıysam hata yaptım arkadaşlar. Onlara dikkatli bakın. Beni de correct edin yani bir yanlış varsa. So that's it. So instead of writing this number, because the thing is, I've written a hexadecimal number and I've put a sign here, a dot sign here, to indicate that the dot is here. So that indication means that to the left-hand side, I'm going to count the powers of the base 16 to something, starting from 0 to positive. And to my right-hand side of this comma, I'll be counting the powers of the base 16 to something from -1 to -infinity. So that's the rule. I mean, nothing changes in decimal numbers or base 10 decimal numbers or base 16 decimal. It doesn't matter. So actually, I can. The thing is, this is 4 bits, 4 bits, 4 bits, 4 bits. So I can represent this number in a 16 bits register just like this. So this is A, B, zeros, and 3. So that's the number. That's how I put it in the registers. So if this is a 16-bit number, it's kept somewhere in the registers. However, there are no place to put the dot in the registers because as you can see, there is the dot. Where is the dot? The dot is here because it was here, right? The dot is here. So I don't know how to represent this. Instead, I can say that this number was already the number without any decimal things times 16 to minus 1, right? Because that's the number of digits before the dot. Or let me put it in a clearer way, in decimals, maybe not to confuse you. So instead of writing this decimal number, I can also write that, right? Or in hexadecimals, I'm going to give you the same example. So imagine I had the comma here. I could say that any questions about it? Something silly that these are not dots. Maybe I should use the. Any questions? Oh, simple. So guys, what I'm going to do is I am going to create a fixed point notation, which means imagine I've got a system. In my system, I have a microprocessor. I can keep 32-bit integers there. That's what I already do, by the way. It is like I'm creating a hypothetical example, but it's not hypothetical. Our system has 32-bit numbers. Let me write them 32-bit. Sorry, that's 32-bit numbers. So all the numbers in my system, sorry, are 32 bits, right? Which means in hexadecimals, they are represented in 8 bits. 8 nibbles. Sorry, 32 bits, 8 nibbles. So any number is like A, B, 0, F, 2, 1, C, 0. 8 nibbles. What I say is, I want to keep decimal numbers in my system. Because if I don't say anything, I would assume that this is 0 to the 16, 16 to the 0. So this is 16 to 1. But I say that, let's assume that there is that already, sorry, there's a number here, right? Yes. Onu siyahla yazmayalım da kafanız karışmasın. Let's assume that there is a dot here. In every number I use, I'm thinking that, I'm imagining that there is a dot here. In this case, when I calculate these numbers, it will be like this, right? And this one will be 16 to 0. This one will be 16 to 1. So it is like, this is the number. However, when I look at the register, I don't see the red things. I just see this number. I just see this, nothing else. I just see this. Because if I look at the registers, there is no thing here. So what I am actually doing is, I'm keeping the same number in hexadecimals times 16 square. So because this number that I imagined hypothetically, sorry, this is -2, I'm sorry, -2. So everybody gets my point, right? Any questions? Actually, this number is this number. So there is a hypothetical number here. So actually the number at the registers are this larger than this, and which is, by the way, this is 1 over. So actually the number is this, but the number written in the registers is 256 times larger than it. If I assume that every number I keep is 256 times larger than it, actually, I'm keeping a decimal number there with a hypothetical comma here. That's it. So actually, if you do such a notation, this is called fixed point decimal notation. I'm keeping, because there are no commas you can put in a register. Register keeps 32 binary values, nothing else. I can only imagine the dot, the decimal dot, to be somewhere. I am defining it. I'm saying that every number I keep actually has the dot after the second nibble, which means actually this number is the actual binary number times 16 to minus 2, which is 1 over 256, which is actually I'm keeping this much larger version of the number in the registers. Any questions about this? This is called fixed point decimal notation.
Hocam ben sadece bir şey soracağım. Biz şu an sıfırdan bir kod mu yazmak için düşünüyoruz yoksa yazılmış bir şey mi yorumlamaya çalışıyoruz?
What we are doing right now, your friend is asking what we are doing right now. We are not doing anything about a code right now, guys. We are trying to understand how to represent decimal numbers in registers. Because in registers, everything is integers, signed or unsigned. How are you going to represent decimal numbers there? That's what we are talking about. Okay?
Okay.
This will be fixed point decimal notation. And I'm saying that I'm going to write a function with fixed point decimal. Now I'm getting to code. So regarding your question, we weren't dealing with the code up to now. We are now going to deal with the code now. And I'm saying that I'm going to write a subroutine, which is going to calculate e to the x. Well, e to the x is something decimal, right? I mean, the result of e to the x is usually 1 point, 2 point something, blah, blah, 6 point something, whatever. So I need to use decimal values there in any base, because e to the 1 is 2.7 something. So I need a decimal, because I just cannot say 3, which is the closest integer value. That would be inaccurate for me. That doesn't work for me. So I'm going to be using, what I say is, since it's fixed points, and since I have 32 bits, I decide on something. I say that I'm going to be using the last 2 nibbles for decimals. So the fixed point will be here, guys. So if you look at it in binaries, it will be like you have a binary value and 8 binary values after the digits. So it's like, this is the dot of the decimal. This is a binary. So you have 8 bits here. You have 24 bits here. So this one will be 2 to the minus 1. This one will be 2 to the minus 0. And this one, sorry, this one will be 2 to the minus 23, because it starts from 0. And this one will be 2 to the minus 8. This is called the decimal notation. We are talking about how to represent decimal numbers in any base, binary, decimal, or binary base 10 or base 16. Guys, there's something confusing about this. Decimal number in English means number with a dot, right? And decimal is also used for base 10 as well, interchangeably. So don't get confused. When I say decimal, I'm trying to say that it has a dot, whatever base it is. If I'm going to say something about base 10, I'm going to use the word base 10 or base 2, which also means binary. Okay? Or base 16, which also means hexadecimal. Okay, so let's read the explanation of the function. This routine calculates e to the x. Okay, x being the input at R0. So when this function is called, this function subroutine will check R0. And if it is 1, it's going to calculate e to the 1 because e is a constant, right? Now, let's say, let's not make this, we can decide, let's make it 8 because we can change this. This was the example we have done. Sorry. Okay, we continue. The output will be in R5. So the result will be in R5. So if the value in R0 is 1, if so, let me write it here. So if R0 is 1, in R5, we are going to put e to the 1. But 256 times larger value of it. So it will be like 256 times larger value. Sorry. So it looks like a fixed point value, right? It is like R5 is 32 bits. So it will have some values. I'm going to represent them by some values. Let's say F, F, F, F, F, F, F, F. Since this number is 256 times larger, then actually I'm putting the decimal point here because 2 nibbles makes 8 bits. That's what I'm doing it. Because if I don't put any decimal point here, floating point, a fixed point here, in that case, I would be using integer numbers, and with integer numbers, you cannot represent e to the 1. Because e to the 1 is something like 2.7, but I'm going to be writing 2 to the 7 times 256. Let's write it. I'll use the scientific notation. Sorry. I'm going to be writing this number. So it is like this. It's going to be something close to this value. Because now I still lose some precision, right? Because there was something going on after 685, but I'm truncating them. I'm losing them because that's the precision I can represent with allocating only 8 bits for the decimal part, the part to the right of the dot. That's why I'm doing it. So actually, all those explanations were about fixed point integers was for you guys to understand that actually we are doing a fixed point example in this. Okay, so any questions? Okay, so I'm going to calculate e to the x. And e to the x is actually, guys, has a formula. Very simple formula, which is this. So we are going to be calculating this. And actually, e to the x, some guy like 100 years ago called Taylor has found out that e to the x is actually this value, the summation, but summation going to infinity. So it is like, let's write it. It's a series notation. It's called the Taylor series. So it starts with 0. So x to the 0 over n to the 0. This is 1. And this is x to the 1 plus n to the 1. Sorry, this is n. So it's sorry. It's not n to the 0, 0 to the 0, because n is 0 in this case. So x to the 0, 0 to the 0. So what is the, sorry, this is 0 factorial. I'm yazamadım ya. This is 0 factorial x to the 0. 0 factorial is 1. So that's why this is 1. This is x to the 1 factorial. This is, so that's why xx. This is x to the 2 factorial. It goes on like this. So it's a summation. If you do the summation infinite number of times, you reach the exact value of e to the x. However, we don't have to reach the exact value of e to the x because we don't need that precision. Actually, we don't have that precision. I'm going to be doing this for a constant number of times. I'm going to do it for 40 times, guys, in my code, just to let you know. So it is like a loop, right? I'm going to be calculating x to the n over n factorial 40 times, each time changing the value of n. This is a loop that you can write, by the way. And actually, you have the functions for f factorial and power that they were already prepared for you. So if you go below, the factorial we've covered in class, and the power exponential. So power exponential of something is actually multiplying it that way. So if you observe the code, you see it here. So in your YouTube video, you can do it. So it is like multiplying two with each other 7 times, right? 7 times. So you create a loop of 7 times, you can calculate it. And that could be parametric. And actually we have this. Actually, this subroutine calculates the power of R0 to R1 and writes it to R2. So if it is R0 to R1, it creates a loop of R1, size of R1 times, multiplies R0 over itself, and writes it to R2. Good. So using these functions, we can calculate this series sum. But remember, we are going to be calculating 2 to the 8, 256 times larger version. And 256 is actually, guys, 256 is in hexadecimals, this value, 256. Okay, so it is like, let me just show you something. So I'm going to write something in base 10. So for example, is this value, right? Because this is base 10 and you're moving the dots this times. And actually, as you can see, this was base 10. What is this number? This number is 100, right? So let's write the hexadecimal number, BC, times 16 squared. This was the base. It is ABC. Any questions about it? And actually, I'm sorry, I should have put this hexadecimal sign here. And actually, this is also 100 in hexadecimals. So in your base, if it is something base square, its representation is 100. So you're multiplying it with 100 and moving the dot 2 times. I'm multiplying it hexadecimal with hexadecimal 100, moving the dot 2 times. So that's why it's 100. So actually, I'm using 2 points to the right of the dot. Okay, let's see how it works. Let's see how it works. Now, guys, if you look, it starts with a push LR. Any ideas why? Why it does start with a push LR? Anybody would like to answer? Yok mu?
Hocam sorumuzu tam anlayamadım ama sorumuz tam değildi.
The subroutine starts with push LR. Why? When did we start subroutines with push LR?
Diğer subroutine'de kullanacağımız için mi?
Exactly. Inside, we are going to use another subroutine call. And since we are going to call this subroutine with e to the x, BL e to the x, in BL, we have saved the LR to, we have saved the next position of the program counter to link register. So I'm saving the link register to stack. because inside here, I will call another BL. It will overwrite LR. I don't want to lose that value. So that do you remember nested subroutine calls? When you do nested subroutine calls, you have to do this trick. Okay. So guys, what I do is I initialize R5. As you remember, the output will be in R5, right? I initialize it to 0. Why do I initialize it to 0? Because actually what I'll be calculating is a summation. As you can see, summation. I'm going to sum these numbers. If it is a summation, and if you're going to accumulate over a register, then you start with 0. If it's a multiplication, then you make it 1, because you'll multiply over and over it. So that's a summation. And for the identity element for a summation is, not the identity element, I'm sorry, the ineffective element, etkisiz eleman, is 0. And this is R6, which is 256. This is 8, guys. I should change them. So the result will be an integer times the decimal result. Okay. So I start with controlling if x is 0, because I'm going to be calculating if R0 is 0, because R0 is x, right? So e to the x. If x is 0, it's already 1. I don't have to do any calculations. I don't want to. I mean, I can do, but I don't want to. Because, I mean, if this is 0, there is no sum. This sum will start, this sum will start from 0 to 0, and it will only calculate this. I can still use the loop, but I don't want to, because it's so simple. If it is 0 equal to 0, I jump to somewhere where I called and 0. And then 0, I add R6 over R5. What was R6? It was this number, 256. So at R5, when x is 0, at R5, I have 256, which is the correct number I'm looking for. Because this is 1, I'll be writing 256. So it is like e to the x is equal to 0, 0, 0, 0, 0, 1, comma, 0, 0. So it is 1 in hexadecimals. So it's just x equals 0. E to the x is 1. Any questions? It's a bit confusing, I know. Fixed point integers.
Hocam başka bir şey sorabilir miyim?
Tabii ki.
İzniniz olursa.
Tabii ki.
Hocam sadece sinx yazabilmek için soracağım da. Hocam burada irrasyonel sayılarda tanımlı mı?
Good question. Well, that's let's discuss this on. I'm going to answer your question. Don't worry. Let's discuss it in more detail on the office hour. But in computational systems, any system, microprocessor, MATLAB, anything, complex numbers, irrational numbers, as I understand, numbers with a complex piece, are some mathematical definitions on our head. So they are hypothetical. So if you want to represent a rational number which has a complex part and a real part, you keep two numbers. You know if they are complex or not. So actually, no.
Okay.
Actually, no. You know them. You keep them. Okay?
Okay. Thank you.
But okay, don't worry. I mean, we are going to solve it. That makes a sign a bit difficult. You're right. We'll get there. Don't worry. Okay, so guys, okay, if it is 0, no problems. I have this number, and since I know that I have the fixed point decimal comma here, it's 1. Look at it. It's 1. I mean, you can calculate this number. Let's calculate this number. So this is 1 times 16 to 0 plus 0 times 16 to minus 1 goes on like this, plus 0 times 16 to 1. 16 to 0 is 1. 1. Yes, e to the x equals 0 is 1. Good. Will it work for other values? Let's see. Okay. Let's now assume that the number at R0 is 1. Nasıl bir R0 oldu o ya? R0 is 1. which means I'll be calculating e to the 1. That means in R5, I'll have e to the 1 times 256. Let's see. Let's see. So I start the code again. Imagine that's, yeah, actually I have this. So this was the case that I called. We are going to go over the code in debugging mode as well. Don't worry about it. I'll have to do the theoretical part first so that you get to know what's going on. Then we're going to be checking if it really works. Don't worry about it. So it is this example right now. I've written R0 and I've written something to R5 so that I can see that it changes. This is unnecessary. This is a redundant code. It's unnecessary. You don't have to write this. Just let's delete this. And I call the function. Okay, I come inside. I again initialize R5 because I'm going to be doing the accumulation over R5. This accumulation, this function. Okay, and if I check R0, if it is 0, this time it is not. So I don't jump. Now I initialize R7 with 40. R7 will be the n in my formulation, guys. This will be R7. This is R7, okay? So I'm creating a loop from 0 to 40, 40 not included, so 0 to 96, 40 different elements. And I'm going to do this sum. Why not 41? Why? That's a mathematical thing. Let me show you why. So it goes on like this. If you don't include 41, it is something like x to the 41 times 41 factorial. Because of 41 factorial, this is a very small number, guys. And it gets smaller and smaller. So, I mean, yes, if you need extreme precision, maybe you should make this 40 larger when you're calculating this Taylor expansion. But after some value, it is unnecessary for us. We're going to see. Okay, don't worry. Okay. Now, 40. And I save R0 to R3 because R0 is the number that I want to calculate the e to the power of. So it is like I'm calculating e to the R0. I'm saving R0 to R3. Why I'm doing that? Because R0 will be used by other subroutines here. I know that factorial function uses R0 and changes it. So I need to save it somewhere. Because it is not like the function calls you do in C. Because in C or MATLAB, if you send a variable into a function, although that variable name is being used inside, the variable in your space doesn't change. You remember this in C. But in our case, it is not. Actually, R0 is a physical place. If you say R0, everybody will understand the same thing and go there and change it. So BL actually uses R0. I'm sorry, Factorial actually uses R0. So if I'm going to change R0, I'll have to save R0 if Factorial is changing R0. And if I have something valuable in R0, I have this power value in R0. I save it to somewhere, R3, because neither this factorial nor PowerX uses R0. Nobody, R3. Nobody uses R3. R3 is the safe place, but they use R0. I save R0 to R3. Sorry, guys, I get mistaken. I confuse you. Okay, guys, then my loop starts. Actually, that's the loop. That's the loop. This loop that we've been talking about. This is the loop. This loop will start. It will run for 40 times because that's what I decided. So I'm moving R7 to R0 because why? R7 is n. In this loop, I'm going to be calculating x to the n over n factorial, right? So I'll need n factorial somewhere. And this factorial function gets the factorial, the number which the factorial of it should be found using R0. So I put that value, which is 40 now, in R0. And factorial calculates factorial of 40 in R1. So at R1, I have 40 factorial. Okay, at this point. Okay, and I write it to R4 because R1 will be used by somebody again. So I have at R4 at this point 40 factorial. Any questions? I continue now. The x value, e to the x, was saved to R3, right? And I've calculated n factorial. Now I should calculate x to the n, which is x to the 40. I need the x value. X value was provided to the subroutine in R0, but I've lost R0, but I saved it in R3. That's why I put R3 to R0 because power x needed in R0. And I put this 40 to R1 because power x calculates R0 to R1. So at this point, I'll calculate x to the 40, which is 1 to the 40, which is 1, because in R0, that's what I'm calculating. It's 1. And it's put on R2. So in R2, I have x to the 40, right? Now at this point, I multiply R2 here with 256. So R2 becomes, 256 times x to the 40. And I make an unsigned division, guys, unsigned division. So R4 becomes R2 over R4, which is the denominator here, 256 times x to the 4. And R4 was 4 factorial. I calculate this. This was here 40. I'm going to be doing it for 39, 38, up to 0, guys. I'm going to be doing it all. Okay? I accumulate it, and I've got R4, and I accumulate it over R5, because the answer will be in R5. And I check if R7 is 1 or not. Is it 1? No, it's 40. I do this again. In the next loop, what I calculate is, since R7 is 39, what I calculate is this. So 39 or 39 factorial. And I accumulate it over R5. I calculate this value until it is 1. I didn't do it for 0, guys. Because 0, I know what happens is 0, it's going to be 1. I'm going to be adding it myself. It's finished, and I add the 1. And I've got the number. That's how it works. We'll give you a small break. Any questions I will take now. And we are going to do the summation one by one. Okay? In debug mode in KL. Any questions?
Hocam ben hala neden 256 ile çarptığımızı anlamadım. E'den alacağımız değer desimal olmayacak mı? Yani hexadesimale mi dönüştürmüş oluyoruz 256 ile çarparak?
No, actually, by multiplying a value with another value, you cannot change the representation. I mean, representation is something in your head. You can see a number in base 10. You can see a number in hexadecimal. It's your decision, okay? What happens when we do it is, in hexadecimals, it is like putting a, okay, let me try to explain it. That's a good question, and that's a difficult question. Guys, let's see an hexadecimal number. Okay, this is a hexadecimal number. It is no different than a base 10 number. It's a base 16 number, okay? So, I'm saying that there's a dot here. In this case, it means that this will be multiplied by a to the 16. This will be to the 0, minus 1, 16 to minus 12. Any questions about it? No, right?
Hocam buraları anladım.
Okay. So, actually, you are keeping numbers in the microprocessor registers. There are binaries. So, there is this number is 12 bits. 12 bits stay. So Where is the dot? There is no way in microprocessors to put that dot. You decide where the dot is. Okay? So if you want to represent this number in your registers, for example, this number, how are you going to represent this number? It's decimals, 10, base 10. Sorry. Please represent this number in hexadecimals for me.
5 çarpı 10 üzeri eksi 1.
Yes, that's in base 10. Please represent it in base 16.
On- 16 üzeri eksi 1 ile mi çarpacağız hocam? Beş.
If you multiply 5 by, that's another number. Maybe we should learn these annotations now. Let's try to find what is the equivalent number in base 16. What is the equivalent number in base 16? Can anybody tell me? Yes, this is 5 times 10 to the minus 1. What is the equivalent number in hexadecimals? Can anybody tell me? Okay, that's the problematic part. Okay, guys, let me try to put it. That was a good example. So these are base 10. So 1 over 2. This is 0.5. 5 times. Since this is base 10, 10 times minus 10 to the power of minus 1 means this. I want to represent this number in hexadecimals. In order to make it more easy, I'm going to write another number in base 10. This is also a base 10 number, right? 8 times 16 to the minus 1. What is this number? It's again 1 over 2, right? I'm still using base 10. Although it's 16 to the minus 1, it is still base 10. These numbers are base 10. It's a representation, okay? So guys, I'm going to convert this representation to hexadecimals. Right? Okay. And this is hexadecimals and this is base 16. Okay, so if you write this representation, it is like 8 times 16 to sorry, hexadecimal olmadı arkadaşlar. Tabii ki bu binary oldu. Kusura bakmayın. This representation is in hexadecimals 8, right? This is the hexadecimal notation. So guys, if this is the base of it, actually I can, let's write this number at 0.8 times 16 minus 1 will be equal to putting a comma here. So actually 0.5 in base 10, base 10 is equal to 0.8 in this is not base 16. Daha çok mu karıştı kafamız?
Hocam.